Don't worry, I'll try and speak the least amount I possibly can for you guys.
You didn't teach a machine to do the presentation for you?
I did.
Oh, okay.
AI right here. So we'll give it a couple of minutes extra, just because we have people that might be joining us online. I think over in Moline, and we also have people still coming in. So.
My wife and I went up to the fire and
Oh, really? That's awesome. How was it?
It was fun, yeah. I mean,
Yeah.
it was I remember 6 goals.
Oh, yeah.
Penalties. And the shot penalties down in our end. We sat basically right in line with the feeds and mud box on the north end of the stadium, right where the like where the Bears games are, the visitors tunnel.
Yeah,
so on
yeah.
the east side of the stadium. Probably 20 years ago,
That's so cool.
yeah, it was perfect.
Yeah.
So you couldn't see when taking a corner on the other side of the view, but anytime you brought the ball on the right side of the stadium, in a perfect view, Phil Long was running right in front of us.
Yeah.
So, you know, so
Sounds so fun.
Beach
it was awesome.
Snapchat,
Did it have
Facebook, like it's not
They
like
didn't
it used to be
know.
normal that you do it.
So I know
Yeah.
none of
So,
the guys
like,
that played in Euros
you guys have
were
to text
able
me if you
to
want
fly in
something.
yet,
The phone I was using,
but they still had
you sent a picture which was like 10% battery. So
long
I'd send like 3
play
pictures a day.
doing
That's like, this is the most depressing.
yeah,
Like, I played Snapchat, this
like the whole game,
like,
Rafinha
like, otherwise I'm
Bernard,
just filming
yeah.
unnecessary things.
Hernandez. They
And
started the
like,
game
why
out
it had
with
to break like the day before we left, and I'm like, and they're like, yeah, we should be able to be here. And I'm like,
Oh, yeah.
it's his first game back after missing a heavy 71 game.
Oh, jeez.
And he goes there. I mean,
overnighted.
Yeah.
he
Like right
mishandled
now?
a back pass,
Yeah.
and that led to the AC.
They won't give
Really?
you one like in the store.
Oh, yeah.
Right.
Should have seen this.
It was still under warranty, but they said that they couldn't give it
I-
in the store.
It's gonna be really tough.
Yeah. I bet. But yeah.
And then so maybe it's not like their new striker.
Oh, really?
So I mean there was a lot of talent.
Oh, yeah. I mean,
Yes.
even if they're
I think it's Samsung. What number?
I told
Wait, no.
Stacey, I said, you watch this with even some of their under 19 players playing. And you compare that to what we watch with the national team.
Right.
I bet people here's like,
Yeah.
ridiculous for an hour, and I'm like, I'm looking at it.
So that was cool.
Yeah.
That was worth the money. I mean,
I'm jealous.
kind of like, friendly, but it was worth it.
Yeah.
I don't have any trouble with phones. It's the calling. It's the problem.
These phones are really, really bad. But I like everything else about it.
I had 3 for 3 years.
I had a 3 as well.
The battery we got on me 5 years, and I was due for an upgrade a year ago, and I got a new Droid something or because the after I had it, I spilled a full water bottle over it. And it's a better battery, so I couldn't take it out and put it in rice.
Right.
So I completely killed it.
That's what like the 3 you could put SD cards in it, and you could take the battery out. Now you can't.
Oh, that's frustrating.
They have to like there's stuff that the way it's made, like they have to use a tool to open up the
Yeah.
I'm like, they don't get it on phone because I like those things.
Yeah, I'm never gonna buy another phone like that. So I went back to the 3 and I had it for a year, and then I had to upgrade to the 4. So I had the year with this whole year.
more coming in. I think Chad's coming in to join us. There we are. Okay. Is there anyone online or no?
Troy is on.
Oh, okay. Alrighty, so I'm gonna get started. Most people in here probably know who I am. For those of you who are joining us remotely, my name is Jacob Rosenthal. I do the UX research. I'm I guess one of the go-to guys for the Go apps. I've also done a little bit of research with wearable technology and voice command with a couple other people here. So today I'm bringing somebody in to talk about machine learning. This is an extremely important technology for a plethora of different reasons. But right now, we're sitting here and we're lucky enough to be on the ground floor as this is just beginning and as this technology is starting to version. What's important about this is that it's going to be something that is going to be present not just as you would see it on a desktop or as you would see it on a mobile phone, but I believe this is something that will be extremely prevalent in heavy machinery and all over the world as we start to see it basically act as the fuel while the machine that would be IoT and big data and qualitative data analysis and all these other pieces start to come together and work together to create these new technologies, the invisible digital assistant, these ideas of AI, how we can better create diagnostics machinery. So today, Alex was kind enough to offer to come in and talk with us a little bit about that. He has some very interesting and very unique experiences with it. And we're going to sort of try and contextualize this not only as a technology as a whole, but really understand how this fits with Deere now, how this would fit with Deere in the near future, and then also the distant future. It's important to be able to plan ahead for these kind of things, so that's why we have this thing set up. I will let Alex sort of introduce himself. He has a very, like I said, interesting background, and I'm going to let him sort of run from there. But after we've gone through a little bit about machine learning, we'll have a little bit of time for discussion. That might run a little bit after the meeting, but you guys are all welcome to stay and participate in that discussion. Okay, thank you. Well, Alex, take it away.
Alrighty, so as Jacob said, my name is Alex, and first of all, I want to thank everybody for coming here today. Judging by how many plates of pizza there are, I'm not entirely sure if it's machine learning that you're interested in or free pizza, but both are really fantastic causes, so well done. First of all, I'm going to talk about my background a little bit, just so you can see where I'm coming from, and then I'm going to talk about an introduction to machine learning and really get you guys grounded with some key terms that you're going to need to know. After that, I'm going to talk about some software and some hardware that you're going to use. And then I'm going to talk about approaches, and then we're going to have a nice discussion. So first of all, my background. I started here at the University of Illinois, and I had nothing to do with computers in my academic career at first. I studied psychology. I focused on cognitive neuroscience, and I worked in a cognitive neuroimaging lab, and my biggest takeaway is that wetware computation has a lot of flaws. After I graduated, I started doing a plethora of personal research into machine learning, in particular neural networks, which I think most of you can tell that comes from my cognitive neuroscience background in undergrad. I started experimenting with using a deep neural network, which was assisted by an evolutionary algorithm, and also used feature learning, which was all to generate expert systems. And this is all in the pursuit of trying to create an artificial general intelligence, which is Skynet, HAL, all the movie villains. And I thought this would make a great dissertation topic. So in the fall, I'm starting a PhD program in computer science down in New Mexico. I'm not entirely sure if this is exactly what I'm going to do, as I haven't secured funding yet. So, and now I'm going to give you a general introduction.
Is it Mexico State or University of Mexico or
New Mexico State. Here I'm going to talk about two big dichotomies that you need to understand when doing machine learning, and then just some more general information that will help you start to understand it. First of all, what is machine learning? In the simplest sense, they are algorithms which can learn from and make predictions on data. And it's often confused with what's known as artificial general intelligence, which is HAL, Skynet, etc. And this evolved from pattern recognition in Aggie research and computational theory. A few key differences. Aggie does not exist yet. And machine learning can do incredibly specialized tasks well, but it doesn't broaden out that learning into other spheres. But what it can do is it can solve numerical tasks, provided you are good at quantifying data and making sure you're using enough data, and more importantly, the right data. It can solve nearly any task that involves numbers. And more importantly, it will get better and better with each task that it solves correctly, hence the learning aspect. And with work and the right combination of approaches, it can actually teach itself how to learn and how to apply skills that it's learned into other areas. And before I get into what training is, which is in the next, or supervision is in the next slide, I want to talk about the difference between training and supervision. All algorithms are given training at first, which is your initial parameters, your data and what you want it to do, and then depending on your learning type, it'll require then supervision after that. So with learning, what it comes down to is how does the human assist, or what is the human's role in the algorithm? And this is fairly straightforward. Supervision, the human will either check the output at the end of each run, or you'll add in new parameters over time. And this is generally used for simple tasks which are repetitive. The primary advantage of this is that it's fast, and the disadvantage is if you're lazy, it requires supervision. And I'm also going to talk about visibility here and here, and this is white box, and I'm going to talk about that in the next slide. So don't worry if that doesn't make sense now. And the other sort of supervision type is unsupervised, which is exactly like it sounds. You give the initial training, you walk away, and you let the trial run. And this is used for exceedingly complex tasks. The main advantage of this is that it's independent, but it's slow, and this is very often what is termed black box. And white box and black box is basically what we can see or what we can understand as humans. White box, as the name implies, we can both see it, and more importantly, these steps are easily understandable to us. Primary advantage is that it's easy to tweak, but it's generally used for simpler tasks. And the training is often supervised, and generally white box is what you want when the steps themselves are more important than the solution being found. And the prototypical example of a white box algorithm is a decision tree, which I'll get into later. Black box is the opposite. You can look at what happened, but it will very likely be hard to understand, or just downright ugly and almost Lovecraftian or Cthulhu's, if you didn't get that previous reference. And the primary advantage of this is it will find a better solution. But like I said, it probably won't be a pretty solution, because with black box, the solution is more important than the steps. And the obvious disadvantage of this is that if there's a problem, it's a bit harder to see what's wrong. That being said, with black box, generally the problem is not the algorithm, the problem is the operator, either misentering data or using the wrong kind of data or not using the correct parameters. And as one would guess, this is often unsupervised, and the best example of this is deep artificial neural networks, which we'll get into. And what kind of hardware can you run machine learning algorithms on? Well, the great answer is almost anything, even something as cheap as an Arduino, all the way up to a very fancy, little bit overpriced, specialized Beowulf cluster, which I built just for machine learning. And like I said, they can be run on anything. They can run on this laptop here. They can run Arduinos. They can run on real fancy stuff. Just the more processing power, the quicker your task. And before I want to get into software, I want to mention that it's going to depend on two things: the specific approach you need and the task being used for. Because those two things, particularly the second, are going to inform your choice of algorithm or algorithms. And for most of these approaches, you're going to want to build off others' work because there's no need to reinvent the wheel. And this will become especially true with artificial neural networks, which I'll discuss in a bit. And there are a few really great and most importantly free and open source programs that you can use to start experimenting with machine learning. One of the best is scikit-learn, which runs in Python, which is great. I love Python. It's very powerful. And what's really nice is it has a whole bunch of great toolkits that you can add on. One, for example, is scikit-image, which is a really fantastic program for doing image recognition and machine vision. Then another is orange data mining, which is a little bit less robust, but it's really great for an intro because they have phenomenal data sets, tutorials, and more to help. So it's a really great way to get your feet wet. And what's really nice, what I really like about orange data mining is that it has this really great pipeline where you just start with your file and then you apply your process and it just shows the output as you go. So that's especially helpful to people who just want to understand the process more than jump in and solve some great questions. And finally, another program is Weka, which is really easy to use and has great tutorials. To me, the downside is that it uses Jython, which is just tweaked Python to seamlessly integrate with Java. Like I said, I'm more of a Python nut than a Java nut or a halfway between Python and Java nut. So. And finally, I just wanted to especially mention the Natural Language Toolkit, which is a toolkit that you can add to scikit-learn. Like everything else I talk about, it's free, which is great, and it uses Python. And what this really excels at is natural language processing. So it can do a lot of different things from developing parse trees, which is this fancy looking diagram that you see here. That's just a great way to really understand how an algorithm is processing spoken speech. And it can also identify named entries and tokenize and tag text. So if you want to do natural language processing, I really recommend this Natural Language Toolkit, which, like I said, is an add-on to scikit-learn to get started. So when you're doing machine learning, it varies a bit by approach, but there are generally three big steps that you want to go through. First of all, you're going to start with your raw data. As one would expect, the more data you have, the more processing time. This can be circumvented by spending more money and getting better hardware, but one of the best ways to reduce processing time is to make sure you have the right data. At best, junk data will make your process slower. At worst, it'll lead to wrong answers and an ill-trained algorithm, which you then have to delete and start over with. So like any area of science, isolate and control for variables as much as you can. After that, you're going to want to hypothesize a model. And I'm going to talk about the approaches in a few slides. And sometimes one approach will fit well. Other times, you're going to need to combine approaches. And then still other times, if you have an odd specialized task, you very well may need to use an approach that is not typically suited for that task. And machine learning works better when the operator uses human learning. And after that, you're going to want to run your algorithm. So like I said, you may be using one or you may be using more. And what's notable about this is that you will fail, you will misapply algorithms. It happens to everyone. I spent probably a good month of not getting anything done, of just focus doing work and then deleting work, which is always fun. And whether your model that you choose is supervised or unsupervised, you're going to have to train it, which, if you recall from a few slides ago, is initial data entry and just setting your parameters. And after the algorithm runs, of course, you're going to want to check the answer, especially if you're just getting started, because like I said, you will misapply algorithms. And so if you're running a white box solution or a white box algorithm, you can go ahead and crack open the box and take a look at what happened because you'll understand it. And if you're running a black box, it would be better to check your parameters or your data, because if you do understand the steps of the black box, it will be very ugly and it will just dishearten you. And like I said earlier, good, easy-to-use algorithms can be run on anything from a laptop to an Arduino, all the way to big stuff. And the best way to get started learning about training is just to go ahead and get started training. Alrighty. So the first three processes that I'm going to talk about are largely used to pre-process data and free up some work from the human operator. So feature learning is one of the most important, and it's something that I use all the time. It can be supervised or unsupervised, and for the structure is basically what it does. It gives labels to raw data, which saves the operator a lot of time. And to train this, you're going to label your input data initially, and then give parameters that you want. And if you're using it as a supervised model, you're going to want to give feedback, or for some reason, if the conditions have changed, then you're going to want to put in the changed data or changed conditions. And this tends to be pretty white box. It's pretty simple and easy to figure out. And like I said, this is one of the approaches where you want to prep the data for other stuff. And this eliminates a lot of work by the person. And another great pre-processing algorithm is clustering. And this is supervised. And it's white box. It's really, really easy. It's just numbers. And while there are many different types of clustering, the clustering of particular note to machine learning is what is called centroid-based clustering, which creates Voronoi cells, which it not only separates these in these nice color-coded segments, but it also has these lines, so you can incredibly clearly see where the delineation is. And to train this, you put in your data and you put in your parameters, and you let it go. And the supervision for this is interesting because you're going to choose between external and internal evaluation. So if you're evaluating internally, you're taking some aspect intrinsic to the data, whether specific data points or just something about the nature of the data itself, to evaluate if the trial is a success or a failure. And if it's external, you're taking other data or information you already know, something outside the data set. And this is a great way to very easily categorize variables. And just like the previous one and the next one, it's a great way to pre-process data.
So Alex, when you say pre-processing, are you talking about the things you would need to do to clean up a data set before you run it through one of the other machine learning techniques? Okay.
Yes. Alrighty, and finally, support vector machines, which is supervised and white box. And this is a model that identifies for you which of two categories that a new example point of data will be put into. And to train this, you give your training examples as well as binary categories you want it to go into. And the usage of this technique could be combined, especially with other approaches, to identify whether a given day is a plant versus not plant day, or a harvest versus not harvest day. Alrighty, and association rule learning. So it is supervised, and it's generally white box. And what this does is add inputs together to predict an output. So to train it, you're going to give example inputs and outputs. And for supervision, just use common sense. If things don't make sense, then there's probably a problem. So, and like I said, this is generally white box. So if there is a problem, it's very easy to figure out what went wrong. And the best usage of this is marketing. This actually came from a master's thesis where the technique was developed to determine if a given customer purchased both potatoes and onions, then they would soon buy ground beef and make hamburgers.
Is it always so cut and dry though? I mean,
As in
like,
this specific one, or
well, with that marketing example, you know,
Oh.
like if customer buys X and Y.
oh no, I mean it's not.
would be interested in seeing-
It's not 100%, but I mean a good association rule learning algorithm will probably find at least 80%. Nothing ever certain, especially with buying habits. And then decision tree learning, and this, as I mentioned earlier, is the very best example of white box, because we have all done this. I don't know if you remember in grade school biology, the dichotomous keys. Say, does the bird have red feathers? If yes, go down that tree. If no, go down that tree. And this is obviously supervised. And the structure of this, as you can see, is just simple binary branches of yes, no. And to train it, you start building the tree and making categories. And to supervise it, you want to check the accuracy. Because eventually this will start building these on its own, and more importantly, it'll give you these fancy numbers. And what this tree is specifically is a survival and mortality calculator for voyagers on the Titanic. And this can be combined with other models really, really well. And I'm going to mention a few great instances of this later in the presentation. Or it can just be used on its own to calculate an instance. And this would be really good in diagnostics manuals and determining what service a piece of equipment needs. And then intelligent searching. This is unsupervised and it's white box. It'll tell you what the parameters that it's determined to look for. And this is used to give the best routes and best points in a given environment. Because an agent is told to maximize its long-term fitness, or long-term reward, in an environment. And so this plots out how best to do that. And to train it, you want to give the search parameters, which will evolve over time. And this could be used by drones to fly over fields to note problem areas, which may not be able to be seen from the ground or can't be easily picked up just with the naked eye. But if you are flying over your field and you see a crop circle, you've got bigger issues. Alrighty, and machine diagnostics. So this does exactly like it sounds. It makes understanding when a problem is going to occur in a machine much simpler. So if you're driving your heavy equipment and you hear it ticking, that means that there's very likely an issue going on. But what machine diagnostics does is it takes that a step further, and it will note that most of the time before that ticking, which is X error, there is also for example, a rise in temperature in Y component. So you note that there's an error before you could with your human senses, which means faster repairs, less damage to equipment, all sorts of good stuff. And to train this, you're going to give the conditions that usually lead to failure, and the algorithm will find more as it learns. And we can think outside the box and apply this to things that aren't just machines. So to larger systems like aquaponics or a crop plot, just note that the larger the system or more open a system, i.e. aquaponics versus a large plot of land, means more variables. So you have to make sure to control for those, and if something is a junk variable, don't include it. Yes.
So in terms of, let's say we are talking about like an engine in a tractor or something, right? When we talk about variables there, would that be, say, we have measurements, 10 different temperature measurements from different locations, we have RPM sensors and things, would each of those come in as a discrete variable then?
Yes.
And is that kind of the totality of the variables that would lead into that, or are there also other things that would be variables?
Well, I mean, I would imagine that for as complete of a machine diagnostics algorithm, maybe to include variables about the weather. Higher weather equals more chance of overheating. But generally, less variables the better. But if it's a good variable, all it will do is cost you more time. So providing you're separating between good variables and bad variables, more is good, or more is better.
Are there any rules of thumb or anything for like determining a good variable, bad variable, or is it like you're saying mostly common sense and understanding of the field?
Yeah, mostly common sense and understanding of the field.
Okay.
Then process modeling and control is another unsupervised white box algorithm. And what this will do is you model a program or you model a process, and then this will refine the process for you and note inefficiencies. And to train it, you want to give the base attributes of the process. And this is one of the few algorithms where truly more data is better. But again, don't put in completely random data, but this one will be especially helped with the inclusion of more good data. And like I said, this can be used to improve a process from planting to harvesting. Really, anything that you can think of that could be refined, it can probably do. For example, if a multinational agriculture firm were purchasing a precision control company in Tremont, the algorithm could analyze the modeling. I know about that because my dad works for Precision Plant. He's one of the programmers over there. So.
For this kind of thing, do you have to specify up front like a cost function so that it understands what's efficient versus efficient?
Mm-hmm. Yeah.
Like, so would that be classified as structure or training?
That would be. Do you mean supervision versus training, or? Oh, I see what you're saying. So by structure, I mean like just generally how it works, and then the training is the initial stuff that you put in. So yeah. So cost benefit would be then training. Alrighty. So then reinforcement learning, which is unsupervised and white box. And this is where an agent also plans to maximize long-term reward. And this is mostly used in fancy robotics obstacle courses and pathing and all kinds of fun stuff. And for this, you want to give the environment and the conditions that lead to long-term reward. And this is really great for pathing. Everything from getting the aerial view of a field for a drone in terms of what is the best points that it should capture and what is the best route that it should take between the points, or use it to produce best arrangement and spacing when planting. If you live on or if your plot is a perfect square, that would come in less. But if you're planting on a trapezoid or something fancy, this would help a lot with making sure you're getting maximum yield. And finally, evolutionary algorithms. We're now going to talk about my two favorite approaches. So evolutionary algorithms are unsupervised, and as a whole, they're black box, although if you look at individual parts of the process, they can be white box. But that is quite time consuming. And as you can guess, this mimics natural selection with using mutations to generate new phenotypes and genotypes in successful instances. And to train this, you want to give the parameters necessary for the task. And this can be used to generate almost anything that requires creativity. And here I found a nice picture of an evolutionary algorithm versus a scientist. And I think the evolutionary algorithm is going to win. It's had billions and billions of years to refine itself as a process. And like I said, this can be used for almost anything. Everything from marketing plans, better bridges, evolved antennae, which is this. This antenna was generated entirely by a computer with no human intervention, and it is a fantastic antenna, and better than anything that a human could have designed with those same parameters, as far as we know. And it can even do machine sequencing, and most importantly, it can also do neural network design, which I'll get to in a few slides. And this can be used to design just about anything, given the proper parameters and creativity. The only limit is how well you quantify data and how well you write parameters and your ingenuity.
Those are some pretty severe limits, though.
Right?
Not for me.
I think you recall maybe like fourth or fifth slide or so, I said machine learning is best with human learning. So. And there are a couple different great evolutionary algorithm softwares to use, or software packages to use. So if you use R, GenAlg package is great. It's free, and it has a really nice visualization tool. Visualization add-on called ggplot2. And then if you are a MATLAB user, the Global Optimization Toolbox is really great. Big downside, it's definitely not free, but if you're a MATLAB user, you already know that. And if you are a MATLAB user, already invested the time and more importantly the money to become a MATLAB user, then this very well could be a great option for you. And I just want to mention again scikit-learn. It can also be used to generate great evolutionary algorithms. And like I said earlier, it's free and it's Python, so you have nothing to lose. Alrighty, and artificial neural networks is one of the most commonly thought of instances of machine learning, and with good reason, it can solve a whole bunch of questions. And depending on the number of layers that you have, it's going to be black box or white box, and that can also be supervised or unsupervised, depending on the number of layers and the task you want it for. And this mimics a group of artificial neurons which utilize connectionist theory. And the main things about artificial neural networks, the two key terms, are weighting, which evaluates the weighting of the connections, and the layout or topology. There's a couple different terms for it, which just means how many layers you have. So in all artificial networks, you have what is over here, this sort of invisible part. That's your input data, and then here are your input neurons, and okay, this is your hidden neurons, which it used to be there was not hidden neurons in artificial neural networks, and then they found out that even one just makes it vastly better in all sorts of ways. So basically no one uses one without a hidden layer. And then you have your output neurons and your output somewhere over here off the slide. And to train this, you want to give inputs and desired outputs. And this is really fantastic at pattern recognition, which note that that is an extremely vague term. And almost anything where we use numbers or machines or science or technology consists of patterns. So it can be used for all sorts of stuff. And this is also really great for modeling the relationship between an input and a desired output. And then a deep artificial neural network is one that just uses what's called deep learning, which simply means more than one hidden layer. Like I said, it used to be just an input layer and just an output layer, and then they started calling things with one hidden layer a deep artificial neural network. But since it's been found out that there's no reason not to use at least one, now deep is applied to more than one hidden layer. And this is really great for computer vision and speech recognition. So if you want speech recognition, this is another really great path to go down. And obviously, the more hidden layers means the more processing power needed, or if you don't have greater processing power, just more time. And it also means that more black box it is. And then neuroevolution, which is my favorite process, and basically it combines the top three, in my mind, which are used for all sorts of general stuff. So it consists of a deep artificial neural network, so remember more than one hidden layer, and an evolutionary algorithm, which develops and refines your deep ANN. So the evolutionary algorithm, what that does is before you even start working with your deep ANN, it's going to use mutations to generate the best possible structure of a deep ANN to use what you want. And structure being both weights and topology, like I talked about earlier. And this is obviously very black box. And what it makes a choice between when having mutations is between the weights. Remember, that's the weights between connections, and the topology. That's number of hidden layers. And then there's a bunch of other stuff here about symmetry. I would love to answer more questions about that, but that would be a bit more than just to go in on one slide here. So, like I said earlier, I'm using neuroevolution for an evolutionary algorithm to generate and monitor a deep ANN, which uses feature learning. So I don't have to do a bunch of data processing either. To teach an ANN how to create its own expert systems, artificial general intelligence. And a really great program to use if you want to try out neuroevolution, again, it's free, nothing to lose, is NEAT, which is Neuroevolution of Augmenting Topologies. And sadly, it is C++ and not Python, but that is its only drawback. And like anything else, there are a lot of ways that you can work with neural networking. You can build your own, which is very time consuming, and it's just a lot easier to start off others' work. And so one of the best ones is PyBrain, and you can do a lot of great things with PyBrain. Reinforcement learning, support vector machines, decision tree learning, all kinds of stuff. It's very easy to integrate into other programs, and it's flexible, it's easy to use, and it uses Python, and it's free. And then another great one is Theano, which also uses Python. It has better documentation than PyBrain, and it can be run on a CPU or a GPU, so it's really easy to scale up your processing power. And then if you want to do some vision tasks, Cough is another great option, but is in C++. Slide switcher.
Sorry about that.
When you say vision tests, what do you mean?
Like machine vision, intelligent search, but mostly machine vision. Yes.
So when you say AGI, how do you compare that to another term that I've familiar with in the past called
Yeah.
strong AI?
Yeah. It would be like a strong AI or unshackled AI, seed AI.
Okay, there was some distinction, because
Yeah.
sometimes with strong AI, they were kind of talking about making something that actually like understands semantics, and things like we do, but like the AGI, I mean, it's like a little more general, basically algorithm.
Well,
But-
so the difference is in terms of how it can apply what it's learned outside of prior tasks.
Is there any notion of the AGI like actually thinks like a sentient being?
Yeah. I mean, they
I mean,
don't.
to me, it
exist.
doesn't sound like it does. Do you think that?
Well. So. Do you want to talk about this after the
Yeah,
presentation?
sorry.
'Cause
I have to
it-
leave early for a meeting.
It'll be the.
I'm sorry,
Okay.
I was
all
gonna
right,
ask
well,
at the end, but I have to leave. Maybe I'll catch you after my meeting.
Okay. Sounds good.
Okay,
And then also
sorry.
my emails at the end of the slide. So, all right. And then another great one is TensorFlow, which was built by Google. So if you really like the Google ecosystem and just love everything about Google, this is a great option. And what's really nice about this is it has a great, easy-to-use GUI. But it is C++, and it is one of the slower neural networks I've found. But if you're interested in having a great GUI, like I said, this might be your best option. And then finally, MXNet is the last one I'm going to talk about. It's C++. It is extremely fast. Not like 5 times as fast or anything, but definitely one of the fastest neural networks that I've worked with. It is C++, and part of what makes it so fast is it's extremely modular. If you don't think part of the MXNet gestalt is going to help you, you can very easily get rid of it and save yourself some time. Alrighty, so I'm going to talk about a couple different combinations that I feel are valuable. And then after that, we're going to have a discussion where if you guys want, you could, because I know more about machine learning and less about agriculture, so you guys could propose me some ideas that you're thinking of, and I could, propose you some steps to go through, some programs to look at, some approaches to take, to maybe go into look into, or even achieve what you're looking to do in agriculture. So like I've mentioned a couple times, field observation by drone is, as I understand, quite important to agriculture and something that I find very fun. Drones are fun. So you're going to want to use reinforcement learning, and like I said earlier, given an environment and what maximizes long-term reward, or long-term gain, this will determine points and routes. And then you're going to want to use intelligent searching, and that will, provided it's done right and programmed well, and you've entered in proper parameters and let it learn well, then that will allow it to search for what it's looking for better than the naked eye. And then, based on my studies of agriculture, which are quite scant, I've read that soil sampling, particularly nitrogen, is important, and that this sampling labor costs more than the actual test itself. So my solution to that is to make it faster, make it cheaper, and make it automated. Once it's all plotted out with reinforcement learning, you can use process modeling and control to improve the hydraulic core sampling technique. Oh, thank you. Alrighty. And I know that there's a really great soil model that's needed, which would adjust to crops, crop type, moisture, pH, weather, technology used, fertilizer used, just everything. But like I said, with everything else, more good data is great, but make sure you're not including garbage data. So isolate out variables that are not helpful. And this would use the most efficient amount of fertilizer. Because if you overuse fertilizer, you waste money on fertilizer. And if you underuse fertilizer, then you waste money on crops and don't get as much yield as you want. And then another conundrum that I've found from my research in agriculture is when to plant, most importantly, but also when to harvest. So this is a bit more complex, and the pipeline that I would use to look into this would be to input your data and label it using feature learning, because that'll save you time. And then you're going to want to use clustering and like those Baroni cells that I talked about earlier to separate into good, bad, and mediocre planting days, say for a 2 or 3 week period. And then you need to reach a decision tree learning algorithm in order to reach an actual decision. And what would be great about this is that it could be automated and run daily, taking into account upcoming weather patterns. So, for example, the combine could text the user, today is 72% chance your best day for the upcoming 2 or 3 weeks, and then if you miss that, like I said, you can have it just run automatically daily by the combine, and it would text you and say, all right, you missed, yesterday. That being said, Thursday coming up would be 62% chance your best chance for the upcoming 2 week cycle. Yep.
The output from the growing cluster would be good, bad, mediocre. What would be some of the labels that you would get out of the feature learning?
Well, so the labels for feature learning, like I said earlier, to initially train feature learning, you're going to want to give data and labels. But then what you put in a whole bunch of numbers, and you'll have moisture level, temperature, pH of soil, crop. I mean, you guys know better than I do all the different variables that go in. You put in a number of those, and then after you've put in enough and used a feature learning algorithm appropriately, you won't have to label them anymore.
Okay, but what would some plausible labels be that you, like, if even if you're manually labeling it at first, like, so say you have moisture, like what kind of, would you label it as like wet or dry, or like what, I'm just trying to get a feeling for what a label would look like.
Oh, okay. Well, so the feature learning, it won't evaluate a given data set in and of itself, but so say you have, I don't know, 20 variables for each given day. And if you do it, 20 times and you use that algorithm, each of those 20 times before you use the algorithm and unleash it, you have to put in, moisture was, X percentage, the crop is this, so on and so forth. But then after you use feature learning and use it well, you won't have to label them in the future. Does that make sense?
I think what he's asking is, how do you determine good day, mediocre day, bad day when it's so all these things are not modularly saying this is good wet, this is bad wet.
Okay. Oh, you were asking about clustering. Okay, I see what you're saying. Okay.
Is that what you were?
Well, so the feature learning goes in that you, after that you do the clustering.
Yeah.
So I guess, so if the output of clustering is to cluster in the good, bad, and mediocre, so then I'm just trying to figure out, like, so you say that the data gets labeled by feature learning. What kind of labels, what is a label?
Yeah, so a label is, because data generally numbers, but it's the labels that the operator puts on the numbers that make it make sense.
Okay.
And it is very time consuming to put in the numbers individually. But if you have a good enough feature learning algorithm and you've used it correctly and applied it well, then you won't have to put them in individually. You can just put them in as batches as you go, and it'll separate them out into the respective features. Does that answer your question?
It can maybe wait till after.
Yeah, we can talk
like a
about it.
whiteboard example of what.
Okay,
would
sure.
help you, like what the output of feature learning. I guess. Yeah.
It sounds like it's you're just tossing in a data set with a bunch of information. It's kind of like organizing it out for you.
Yeah, that's a great way to put it. It sort of organizes it for you.
Okay.
Alrighty, and so now we can have a discussion. So this is my website, and this is my email, because I am an extraordinarily creative person. If I can't answer a question today, due to me just not having enough information or not understanding the question or whatever, feel free to shoot me an email or think of a question at a later date. I am always happy to help. And then on my website, I have a couple tutorials. I have a artificial neural network code that's ready to go on an Arduino. Just load up your Arduino and put it on, and you'll have to enter a couple parameters, but then you can get to work and start using it.